So the next speaker is Frick, and he's going to tell us about formalizing Thomae's function in Lean.
All right, hi everybody. Today I'm going to be talking about formalizing the Thomaes function in Lean. So why do we care about the Thomaes function? The Thomaes function is a standard counterexample from real analysis. It has the following two properties. It is continuous at every irrational point and discontinuous at every rational point. And I've included the two theorems which I proved over the course of the project. And I think the essence of this counterexample is to show that continuity can have some very weird and sort of unintuitive properties. So why did I choose this project? Thomaes function is in almost real analysis textbook I've seen. It seemed to be the sort of thing which most mathematicians will see eventually. It also seemed to be a suitable problem to tackle in terms of scope, and was also in proportion to my Lean skills. And this third point, which is pretty cool, is as far as I'm aware, there is no previous computer verified version of this proof. So it's another brick in the ever-growing wall of bits of mathematics which have been formalized by computers. So let's go right to the definition of Thomaes function. So Thomaes function is defined on the reals, and it has two main values it returns. If the input to the Thomaes function is irrational, it returns 0. Otherwise, if the input to the Thomaes function is a rational number, it returns 1 over the denominator of the input, where in reduced rational form. And in the middle here, we have the equivalent definition Lean. The thing to note here would be is that in Lean, due to the construction of rational numbers, the numerator and the denominator are guaranteed to be in reduced form or co-prime. And so that bit of information isn't necessarily needed to be encapsulated in the Lean definition. So below here, we have a point, or we have a graph of some of the inputs and some of the outputs to the function. I think it's pretty helpful to, at a quick glance, sort of get an understanding of what the function is doing. Notice too at the bottom, that solid line is all the irrational points, which are 0. So the way I've been thinking about this presentation and what I want to showcase is, instead of giving an overview of the entire project and all the different sublemmas, what I want to do is specifically focus on the part of the theorem where we prove that the Thomaes function is continuous at irrational numbers. And the reason I want to do this is I want to highlight the process of comparing the paper proof to the computer proof, and sort of showcasing some of the interesting design choices that were made and things that happened as I was going through this proof. Okay, so given a x and epsilon, which are in R, epsilon is positive and x is irrational. Here's sort of, this is the equivalent first bit of the proof in Lean. Something interesting here, this is like the first gotcha I ran into, which was different, is that in Lean, the definition for continuity is more topological. Thomaes is usually seen at a more introductory level to real analysis. And thankfully, Lean has this escape hatch in the metric namespace, which allows us to take a standard epsilon delta style proof, and it will take that proof and convert it into a proof that satisfies Lean's definition of continuity. So at this point, here we have our goal statement. Right after we call the metric continuous at if, we simplify as much as possible, and it simplifies some of the distance functions at the end, and then we introduce our epsilon and epsilon positive. In this next bit, consider some natural number r, such that 1 over r plus 1 is greater than 0, but less than epsilon, since epsilon is a positive number. The idea being here, for any positive real number, if you have a sufficiently large denominator, you can find a fraction of the form 1 over that denominator, which is less than epsilon. And this is how we express it in Lean. An interesting note here is that the way that Lean encapsulates the fact that R is positive is it returns, where it produces a number which is R plus 1. And since for any natural number plus 1, it must be positive. The idea being that we want to construct a delta such that the distance between a rational q and x, if it is less than delta, would imply that r plus 1 is less than or equal to the denominator of q. And the reason we want to do this is, if you'll recall, since the Thomaes function for rational numbers is defined as 1 over the denominator of that rational, we can essentially apply the transitive property of less than or equals to and less than to show that the Thomaes function at that rational is less than epsilon. The paper proof creates deltas of the following form, where k of I is a natural number such that k of I is less than I times x, which is less than k of I plus 1, via the Archimedean property, for I equals 1 up to r plus 1. And this was the first bit in the proof where following directly the paper proof was pretty painful. What was particularly painful about it is, since we're invoking this existential, doing this over an index becomes cumbersome, especially as you have to start proving other sublemmas. Proving things such as that delta is positive, or as we derive the inequalities later on in the proof, always appealing to this Archimedean property was way more painful. And so it was at this point I said, okay, stepping back, can we find a more compact way of representing these delta i's? And in fact, we can. K of I must be exactly the same as the floor of x times I. There is sort of the inequality. There is the inequality which we derive from this. And what's really nice about this is we get a very compact representation in lean as a lambda function. And it's as simple as the following in the middle of the slide. This also has the benefit of allowing us to use the Floor API to prove a lot of the lemmas we need further on in the proof. I also found this to be a more motivated approach. So if you look at the floor of x times I over I and the floor of x times I plus 1 over I, and you imagine I as successive powers of 10, those become quickly recognizable as decimal approximations of x. And so I have a video here on Desmos showing that. And it's the sort of thing where, because the Archimedean existential was painful, it led me to try something a little bit different. But with the added benefit, now that we have a very clear description of the relationship of the index I to the actual left and right side of the inequality, it makes it very readily available to visualize, which I think was a cool benefit of doing this. Continuing with the proof, we want to choose delta, which is equal to the min of delta 1 up to delta r plus 1. We do this using the set exists min image function. And this gives us, well, first of all, we need to give a proof that the indices which we're looking at are finite and are non-empty. And this gives us the indice, which is the minimal delta I. And in the statement below this, with a refine, we are telling lean to choose this delta I at the minimum indice. We're giving a proof that this delta I is positive, and we are then receiving an x1 and x sub 1 point, as well as the delta hypothesis. And below this, I've included the type signatures in the list of hypotheses in the goal statement here. So after this, we're now at the point where we want to prove that the distance between x sub 1 and x is less than epsilon. We split by cases based on whether x sub 1 is irrational or rational. In the case where it is irrational, it is very easy to prove, because you end up wanting to show that the absolute value of 0 is less than epsilon, which is true because epsilon is positive. And so we focus on this case where x of 1 is a rational number. And so how do we tell lean that no rational with a denominator less than r plus 1 can fit into this delta interval around x that we defined? And we can use the following lemma. So if you imagine an open interval such that both the endpoints are rationals with the same denominator, and their numerators differ by exactly 1, then it can be shown that no rational with the same denominator, regardless of numerator, could fit inside the interval. And this is true because if it did, this would imply that there was a distinct integer between two consecutive integers, if a and b are integers. This was another place where the proof I was working at diverged somewhat significantly from some of the paper proofs I was looking at. And they never mentioned this explicitly. I think this is actually a very straightforward way to get to the contradiction faster. Up above here, we have that theorem statement. And in the middle is that theorem statement applied to the denominator of Q based on the delta i's that we constructed. And so right here in this little block of code, this essentially constructs the fact that r is less than the denominator of Q. And what it does is it goes by contradiction. So we end up getting that the denominator of Q is less than r plus 1. We know that there's an indice which is exactly equal to the denominator of Q is in one of the delta's i's. Because we chose the minimum, we know that the denominator, or 1 over the denominator of Q, is bound on either side by the 2 bits of the delta. And so using this, we directly apply the proof on the previous slide to reach a contradiction. And in this way, we don't need to explicitly use any intervals, which were in many of the paper proofs I was following. And that's mainly what I wanted to showcase. And on this last slide here, I wanted to talk about some of the takeaways I got from working on this project. What I found is that searching for individual proofs on the website is a lot easier to learn than tactics. So it's interesting too. I guess mileage may vary depending on the quality of the proof. But in my case, it was very easy to find lots of great lemmas about sets and intervals, but just based on the structure of the proof, those are not actually the things I wanted to use. And so it's interesting in that it is sometimes the case you can readily find lemmas about different mathematical constructions, but it's not so obvious which is the best way to use for the lane proof. Tactics are also harder to I guess learn or understand. The second other point I learned during this project is that you want to use a div API as much as possible, and then only use the rational API when you need to use specific things to the construction of rationals, for example, such as the fact that the denominator and the numerator are coprime. And the 2 bits that I learned about maths while doing this project is that closer approximations of irrationals necessarily entail larger denominators, and that for a function which has a relationship with the denominator and the output, you can potentially use this in epsilon delta style proof to restrict what values end up in intervals around a delta. And the last bit is I now have a deeper understanding of how the interval exclusion works. I was sort of intuitively reasoning like, yes, like this fraction doesn't actually fit into that interval. But doing this project really forced me to actually understand sort of the exact theorem for why that doesn't work. And at the bottom here, I have a link to the repository if you're interested to look at the code. And that is everything I have to say. Thank you to Kevin Buzzard and Eric for helping me along this project.